You're tweeting, and so what does it mean to actually send a message in a system like this? Well, you want to make it efficient to send new messages, potentially, and you want to also make it efficient for a person who is following several other people to see the messages that are relevant or interesting to them. I can't tell you how many actual paying customers of 10gens are building a system that turns out to be essentially this, right? Essentially a message distribution system. They might not think of it as a message distribution system. They might think of it as an ad delivery network, where publishing an ad is like publishing a message. They might think of it as a dating network, where registering in the dating site is creating a new message, conceptually speaking, a new message that is to be propagated to other people with similar dating profile preferences. I mean, there's lots and lots of applications, if you just generalize a little bit, that essentially are trying to solve the same problem of, you have 10 million of these things over here, and potentially 10 million of these things over here, and you want to show the right few hundred of these to, each of your 10 million people. Okay, so anyway, there's a question of putting the data in, sending a message. There's a question of reading the data back, showing people the tweets that are interesting to them. And so here are three possible approaches. Are there people that already know these terms and know these approaches? I'm willing to admit it. I already know them. I wrote this. Yeah, okay, fine. So PAX is, you can just keep drinking. So, okay. So what are these different approaches? At this point, I'm going to actually start showing you real code. I hope that's not going to scare you. It's trivial code, but it's real. So one possibility is what's usually called fan out on read, meaning what does it mean to post a message? It means you put a document, a record, into MongoDB, and what does it mean to read all the messages that are interesting to me? So he posts a message, I want to see my inbox, I'm following him. When I show up to see my messages, I'm going to look for all the recent messages by everybody whom I'm following. So in MongoDB, we have this feature called sharding. It's analogous vaguely to database partitioning in certain relational databases. It's essentially a scaling strategy, whereby you can deploy multiple, mostly independent MongoDB systems. I'm not going to go into too much detail exactly what those systems are, each one of which stores a subset of your overall database. And they don't really communicate with each other, so they operate in parallel, which means that you can get very good scaling out of them, essentially linear scaling. For each such MongoDB shard, you should get one more unit of read capacity, write capacity, but only if you're using them effectively. So, what does using them effectively mean? Suppose that you decide that you're going to have a collection called inboxes, and you want to have the data be parceled out into different sub-areas of your database, different shards within your database, according to the sender of a particular message. So you shard your collection this way, and you build an index on compounds on who the message is to, and you sent them, and the time at which the message was sent. And a message might look like this. So here's a message that goes from Joe to a particular list of recipients, Bob and Jane. It has the time at which it was sent and the content of the message. To actually send the message is basically just one write operation into MongoDB. It's to save a new message. So as I said, MongoDB stores these things that we call documents. A document is, conceptually speaking, a nestable dictionary. So the dictionary has fields, from, to, and sent. Each of the fields has a corresponding value. The string Joe, the field called sent has a timestamp as its value, and the field called to has a nested array, in this case of strings. So this is kind of what a record looks like in MongoDB. I mean, if you generalize, this is an example of such a record in MongoDB. And so you can actually already see that we're making certain choices about what data we're going to put together versus not. So this is actually one record. If you were to model this relationally, you would need at least two different tables. One for from, sent, and message, and then a separate table linking Bob and Jane to this particular message. But in MongoDB, you get to pack this stuff together according to your preferences. And of course, performance profile. So anyway, I realized I need to explain this for people who've never ever seen one of these things before, in case there's any of you here. By the way, all of this example code, in principle, should be runnable unless I've made some syntax errors. But the example code is presented in JavaScript. There's no inherent connection between MongoDB and JavaScript other than that MongoDB itself comes with a JavaScript command prompt into which you could actually key this code. So the point is that MongoDB can be used from lots of different programming languages. The reference language that we use for all of our documentation, for simplicity's sake, is JavaScript, and then that code you can actually just cut and paste into our interactive command prompt. So that's why I'm using this language. Is there anyone who finds JavaScript completely unreadable because you're only familiar with, I don't know, Erlang or something? Okay, cool. So good. Very occasionally I'll meet people who just say, oh, I don't know JavaScript, and they just refuse to actually take the 2 seconds that it takes to figure out, oh yeah, that's I'd have to read that. Okay, so anyway, in a situation like this where what you're doing is you're doing a sort of, you're trying to optimize for the putting of the message into the system. Saving a message is a single write operation. Querying for messages involves looking over the collection of messages by the contents of this array called to. And as it happens, MongoDB can do that. If you ask the question, find me the documents where to is Joe, we will actually, I'm simplifying things a little bit, so don't interpret this to mean anything other than exactly what I'm saying. If you look for a message that says to Joe, then we will, if it turns out that to is an array, we'll look inside the array to see if, oh, this is a typo. This should be to Bob. We'll look inside this array to see if the string is in that array. So the point there is that we can look inside of these nested documents. This is a feature of MongoDB, which often influences your choices of schema design. But the actual read operation here is going to have a performance profile that you might not like. So let me just show you this pictorial. So again, in MongoDB we have this feature called shards. Don't worry too much about what a shard actually is in terms of the mechanics of it. You can just think of them as units. And each one stores a different subset of your data than every other one. So they're like partitions, but with some extra features. So if we're doing what's called fan out on read, that means that the insert operation, the send operation, send a message, is a single document insert. So that's good. We've made posting a message efficient. What about the flip side? What about the retrieving documents that are interesting to people who are following a particular user? Well, in that case, we actually have to do reads from multiple shards, looking for anything that was sent to me, for example. So that's not going to be as, well, it's not going to be as performant, and it's not going to be as scalable. Why is it not going to be performant and scalable? Because the same work is going to be performed in 3 places rather than in 1 place. Now, it might be that each one of these things is relatively fast, but the point is that additional shards are not going to get you any additional work. So this is one way to think about performance and or scalability, which is the work that you're doing something that can be targeted to just one place? If it can be targeted on one place, then every additional place that you add to your cluster is going to be that much more capacity to do work at the same time. So in our terminology and our documentation, we tend to call this kind of operation where a read operation has to go and hit all of the shards in your cluster. We tend to call this a scatter-gather query operation, or or sometimes called a broadcast operation in some other databases. And the problem with broadcast operations is that even if each one of these shards is fast, the fact that every shard has to do the work means that you're not going to get any extra capacity by adding more shards. So it's like if 3 of us all have to take a second to write something down, but for some reason we all have to write it down, then when we add a 4th person and he has to do the same thing, we're still all going to take a second. Whereas if that work was parceled out separately, whereas I did one operation, you did another operation, and you did another operation all at the same time, then we could do 3 units of operation. So that's a thing to understand or to think about in MongoDB with our sharding architecture. When you shard, certain operations can be targeted, such as this send operation can be targeted in the case where you shard on the sender. But then those other operations, the reads, based on the recipient, need to become these scatter-gather operations. So that's not scalable because it's the same work being performed across every unit of capacity that you have. Yes, sir?
But each shard will work on less data, right?
Each shard will work on less data, but one other subtlety about that is that in this diagram, the intent is that each shard is working on potentially less data, but they're doing about the same amount of work. And that's actually in the real world factors are likely to be this way because the dominating, the physical reality is your data is either in memory or it's not. And if it's not in memory, then we have to retrieve it from disk. And that's going to turn out to be the dominating factor. And so if the work has to go to shard 2, and let's say this, whatever this page is supposed to be, if that happens not to be in memory and has to be pulled in off disk, your whole read operation has to run at the rate of effectively your slowest shard if the read operation has to hit all these shards. So even though each one is doing less work, it still doesn't scale in the sense that the concurrent work that's going to happen from repeated load, from concurrent load, is going to have undesirable locality properties. I'll get back to this more later, but this represents a single read. Suppose you want to serve 100 of these at the same time. Then in theory, you have 100 of this diagram overlaid on top of itself. None of them is going to be very fast. Whereas by contrast, and we'll get to this in a subsequent model, by contrast, if each read could go to one shard, then that means that until the point where you're at the capacity limits of each of your shards, you'll get that much more capacity out of your additional machinery. I don't know if that explanation made sense. Did it make any sense?
Slightly.
The other way of looking at it is, suppose you want to have a message, suppose you want to have 3 messages written down.
Are these separate machines?
They are, yeah, of course. I mean, I told you not to worry too much about what they are, but assume that they're not sharing any resources at all. I'm sorry, there was another hand.
I was going to ask, does MongoDB decide how many shards are there? Or
No, you set up how many shards there are.
Yeah.
And physically, these things are ideally separate machines. If you put them on the same machine, well, that's no scaling, right? I mean, I don't know, it'd be like 2 steering wheels on a car. It's not going to make it go any faster. If these are separate machines, then each one is that much more capacity to perform write operations or to perform read operations, but only if they're performing different read or write operations. Yes, sir?
One more question. How does it decide where to put the information?
Well, you decide that.
Okay.
In particular, on a collection by collection basis, in this case I'm saying, for the collection called inbox, whatever the from address is, the sender should decide how to route the write operation. And likewise, read operations can be routed to let's say just one shard if they incorporate the so-called sharding key, which you specify. So the idea of our scaling story is that in MongoDB, you set up a number of these things called shards. Now, in case people really know almost nothing about MongoDB, each of these shards physically should actually be different machines. In fact, they should probably be several machines so that you have redundancy of the data within each shard. Typically, a shard is what we call a replica set. I'm not going to talk very much about replica sets and replication because replication is not a scaling model in MongoDB. Replication is just a durability, redundancy, disaster recovery, availability approach. Adding extra copies of your data is not, let me just dispel this in case you thought that this was the case. Adding extra copies of your data in our replication architecture is not, except in a very, very small number of pathological cases, a scaling story. The pathological cases are really quite pathological, so I don't want to talk about them unless people have specific questions. But each shard should be what we call a replica set, meaning a unit of capacity with redundancy within it. And they shouldn't share any physical resources. They shouldn't share any disks, they shouldn't share any memory, that sort of thing. Once you have this sort of thing set up, you decide on a collection by collection, think table by table basis, this collection should be partitioned up according to this field, that collection could be parceled out according to another field, and then read and write operations that are keyed on the field can be targeted based on some stuff that we have that's not in this diagram. Read and write operations that do not incorporate the so-called sharding key cannot be targeted and therefore have to go to all shards. In parallel, but nevertheless, all shards. Does this help clarify things? Yes? No? Yes? Okay. So, the point of this was that if you optimize for putting messages into the system by saying shard on the sender of the message, then you are de-optimizing on retrieving messages because the reads for all messages to a particular user will have to span multiple shards. So the idea is that the sharding allows you to have an optimization, but you have to be choosy about it. So What's the consideration? You're putting one document into the system per message sent, and you're storing the recipients as an array, which you can query on. But reading an inbox is for finding all messages where my name is in the recipient field. This is a so-called scatter-gather query. And that is potentially a lot of random I/O within each shard, and in general, the answer can't come back until the slowest shard responds. Yes?
Scatter-gather
Yeah.
synonymous with fan-out on read?
No, fan-out on read is a model for how you build systems like this. Scatter-gather is a term that we are stealing from operating system I/O theory. If you like, think of it as broadcast versus targetable, right? In some other databases, they use the term broadcast query versus targeted query. We use the term scatter-gather. I actually prefer broadcast because it's fewer syllables. But anyway, so what about this other alternative, so-called fan-out on write? So instead of sharding on the sender, we shard on the recipient address and the time at which the thing was sent. Well, in this case, same message, same typo. This should say Bob, not Joe. Same message. Sending a message now involves multiple writes into the database. So the idea is that the previous model said sending a message was putting one document, retrieving my inbox was potentially scanning documents from lots of recipients on lots of shards. In this model, I'm sharding on the recipient address, and so in order to put a message into the system, I put a separate copy for each recipient, for Bob and then for Jane. But then to read my inbox, I'm doing a query on, this should say Bob, recipient Bob, and sort by the sent time. So let's see what that looks like pictorially. So to to send a message involves putting as many documents into the system as there are recipients for the message. But to read my inbox, since I'm just one person, I only have to go to one shard. This is a property within our sharding architecture, and it's just a nice feature, which is that if you're doing a query for documents that have exactly one value of the shard key or a range of values for the shard key, like a single range of values, with very high probability that will go to one shard. If it's exactly one value, it will go to one shard, and if it's a range of values, it's very likely to go to one shard. In fact, ranges can span shards, but they may or may not. That's a dynamic property of the system. MongoDB tries to keep the data balanced, in fact, automatically. So, okay, what does this mean? This means that at the cost of by increasing the cost of putting messages into the system, I'm optimizing for the case of reading messages out of the system. So what do people think? Scalable, not scalable?
That's what you're doing more frequently.
Well, what do most systems do?
Read.
Yeah. I mean, if you think about something like Twitter, I don't know how often people tweet. I mean, I tweet exactly 0 times a day, but in principle, you could do it. Well, if I were to tweet once a second, that would be huge. But in principle, you might do it some number of times a day. But if I have lots of followers, even if they're reading at the rate that I'm posting, the ratio of followers to posters is going to determine the ratio of reads to writes. That's a very simple, totally meaningless analysis, but I think the logic was valid. So you get the idea. I mean, lots of systems, I would say the typical web type system, and actually the typical database application, usually does easily 10, 100, 1,000, million times as many reads as writes. So it probably makes sense to think about scaling your reads. Again, like I was saying, think about the problem you actually have to solve, not the problems that you might need to solve. Yes, sir?
If most of your messages are sent to a small number of groups, basically, can you just shard on the 2 instead of having to go the intermediate step of the recipient?
Well, okay, so in this data model, which was perhaps infelicitous, I made some, you can't, so I should have picked a slightly clearer name. In MongoDB right now, for a variety of internal reasons that I don't necessarily want to go into until maybe afterwards, you can't shard on a value that's an array. It's basically like this weird consequence of other decisions that we made. There's no superficial reason why we couldn't let you do it, other than we made some other decisions. So yeah, that's a very good question. So that means that you're following. So Drat, you're going to catch me on my next mistake. Okay, any other good questions at this point, or even bad ones? All right, so to summarize, in this case, fanning out on write is you put one document per recipient of a message, Reading is finding all the documents where I'm the recipient. But since I'm sharding on the recipient, the inbox read will hit just one shard. But here's the downside. You're still doing lots of random I/O. What does that mean? Well, the intent of this picture was that, potentially these are different documents that came in at different time for me. MongoDB makes essentially zero guarantees about the exact layout on disk of your documents. I mean, at least relative to each other. Within a particular document, it makes a lot of guarantees about how the document will be laid out on disk, but one document to the next, they might be stored in the order in which they came in or not. So one way to put it is that MongoDB does not have a clustered index of its data layout for people who are familiar with those sorts of things in relational databases. We do not try to keep the data on disk in some order according to any of the fields within the documents. So over time, it's very likely that your documents will be laid out roughly in the order in which they came in. So the intent of this diagram is to suggest that I might have gotten this document at a certain time, and then other people got other documents, and then I got this document, and likewise. So one aspect of this is that it's very likely to have, if you like, very high fragmentation of messages that are aimed at me. And so what does that mean? Well, if you've heard fragmentation before, if you've heard the term random I/O before, you probably get the idea that it's bad. Why is it bad? Anybody know why random I/O is bad?
Sequential, just have to go to disk.
We have to go to disk. Anybody else?
You have to jump around.
Keep
it in different locations on the screen.
All right, you're all saying things that I think if we stirred them together would be reasonable. Does anybody happen to know how many random I/Os you can get out of a spinny platter? So you know what I mean by spinny platter, right? You crack open an old hard drive, and there's like these little metal doodads with like a fork that sort of moves back and forth over them, little metal plates, right? Inside of a hard drive. Cool. So those things, the fork, at the tips of them, they're called disk heads, and they can only be moved so many times per second. And does anybody know how many times per second a typical modern disk can do? Order of magnitude? Yeah. It takes about 3 milliseconds to reposition the disk heads. Sorry. Yes. Yes. So you can do about 300 random reads or random writes on a single spinning disk at this point. Try it out. There's going to be other things at your operating system that might slow that down, but typically you're not going to get more than a few hundred per second. So if you're thinking, okay, how do I get good performance, i.e. how do I get good scaling? So there's different aspects of scaling here, right? One of them is, okay, this is scalable because somebody else's inbox read could go to that shard, and therefore they can process in parallel. But it's still not going to be that performant because this one is going to be doing all these, potentially anyway, going to be doing all these random I/Os. Meaning that other reads that are going to come to the same shard, right? At the same time, there could be reads for, Fred that goes to this shard and Mary that goes to this shard, but other reads for like, I don't know, Chuck goes to this shard, and those other reads will be slowed down or potentially competing with the disk activity of loading up my stupid inbox messages from the disk. So again, one aspect of scaling is it targetable? Another aspect of scaling is, even within the shard to which the read is targeted, is it performant? And so one of the things that is extremely important for any database, this isn't MongoDB specific, so you're getting some freebies for any data store that you like, is are you doing more random I/O than you should? Can you reduce the total quantity of random disk data? So now we get to the punchline, which is, for this data model, what's a good idea? Well, one possible good idea is fan out on write. So you're still putting multiple documents in whenever a new message is posted. But instead of storing each message as a separate document, you treat an inbox as essentially as an array of messages. And when a new message comes in for me, a new message is pushed onto an array within my inbox. But there's some trade-offs here. There is a maximum document size. There is a maximum size that a single document can get to in MongoDB. It happens to be 16 megabytes. It's extremely unlikely that the universe of, even if I were on Twitter and I had a lot of friends, both of these things are false, but even if they were true, it's extremely unlikely that my universe of friends could produce 16 megabytes worth of tweets, right? 16 megabytes is a huge amount of data when you're thinking about stuff that's generated by humans. It's, bigger than a typical paper encyclopedia, if you remember what those things look like. Even so, there is a maximum document size in MongoDB, and it's something to be mindful of. And there are other reasons to be mindful of this. So what you tend to want to do is, in a system like this, is you tend to not just want to have an array you don't want to represent the entire inbox as an array. You want to represent contiguous regions of time as a single array in a single document in MongoDB. Whoops, that was not intended. And so the idea is you can still shard on roughly the same idea, but you only have to look at a couple of documents to read, or a small number of documents to read the whole inbox. So what does that look like? Well, okay. In this case, I need to have an inbox which has, in this case, I'm calling it an owner and something I'll get back to called a sequence. And then I need some metadata about the user. How many messages have they received so far? So here's the same old message. Sending a message in this bucketed approach involves, we have an operation called find and modify, which is basically update a record and show you the result of the update, essentially. So what this will do is it will get my user document, so the particular recipient of the message, get the document out of the system, increment the total message count by 1. Don't worry about this upsert business. Upsert exists in some other databases as well. And what I actually care about is the resulting message count. So after a new document has been submitted, or a new message has been submitted for me, how many messages do I actually have at this point? And I use this number, my total message count, to figure out where in the sequence of buckets to actually store the new inbox message. And so what I'll actually do is I'll say, okay, how many messages have I actually got? And divide by 50, round down. Once I get my 50th message, that will create a new bucket. And then when I get my 100th message, that will create a new bucket. So I'm bucketing by 50. 50, totally arbitrary, doesn't really matter what the number is, just pick a number. And then to actually put the message into my inbox, I put in a document, keyed to me, and into a bucket that's basically this sequence number. Where, how far into my inbox have I got, containing the new message in an array called messages. And if I don't already have such a bucket, make a new bucket. Okay, that was a lot of hand waving and a lot of pointing at code. The basic idea is this will help me minimize the random IOs, because instead of having to look for lots of different messages scattered all around, all my messages that came in around the same time will be in the same bucket of up to 50 messages. So sending a message still involves writes to different shards, potentially some random IO there, but again, it's extremely likely that reads are more important than writes. Reading my inbox, at least for the last 50 messages, is a sequential read. Meaning that, if you like, I get 300 random IOs per second. I'm only going to use one of them for this operation, at worst. At best, this is already in memory. At worst, I have to do one disk seek, meaning that I therefore have 299. I'm being very precise about these slightly made up numbers. I get to do 299 other ones within the same second. Okay? And I get to do 300 of them over here, and 300 of them over here. Meaning, in this diagram, based on these extremely precise, albeit made up numbers, I can do, even in the worst case where nothing is already in memory, 1,000 inbox reads within the same second. And if I had another shard, that would get me another 300, and another shard, that would get me another 300, and so on. All right. Who's with me? All right, who's not with me and wants to be? If you don't want to be, you just came for the pizza, that's cool by me. Okay, well, nobody's willing to admit that they're not with me. Anybody have any questions? All right, cool. So, all right. This, I think, is, if you got this, other things related, similar. So suppose you have...
I have a question.
Yes, sir.
Is the reason you're less fragmented there
Yes.
That you've declared 50 messages worth of an inbox
Yes.
in one
Yes. Document, yes. As it happens, you're right, I didn't explicitly say this. MongoDB always stores its documents in a serialized, sequential, non-sparse fashion. Meaning that what you see is actually going to be stored on disk in order, essentially, with no holes, no gaps, no pointers out, that sort of thing.
As long as it's a single document.
Yes.
So
Now that may eventually change, but that's how we do it right now. Yes,
so
sir.
what you defined is basically a chunk. So
Yes.
if you've got one message, you've reserved
Yes.
a relatively large block of space. So, but
Yes.
Yeah.
And whether we've actually reserved the space up front or not, that's a little bit more of a dynamic property. But the basic idea is that whatever space it actually takes up will be sequential. Okay. Now, one thing that maybe some of you who haven't raised your hand to either the question, do you get it or do you not get it, maybe what you're thinking is, I've already got SSDs, so I don't care. Well, good for you.
And a shit ton of memory.
That just means that you get a couple orders of magnitude more out of this picture, but the scaling story remains relatively the same.
So maybe you're gonna
Yeah.
follow up with this later, but what happens when you decide to add another shard?
Sure. So it's a reasonable point. So MongoDB sharding, I'm actually, I don't want to go too far over time. Should I try to stick to my 45 minutes, or do you want me to just digressions? And of course, you're all free to leave when you've had enough of my blather. All right, so I might go a little bit longer. So MongoDB sharding is based on the idea that, it's based on a couple of ideas. One of them is we want to give you linear scaling. We also want to try our best, roughly speaking, to try to distribute your load. Now, as I hope has been clear, different choices about what your shard key would have different properties for how your load gets distributed for reads versus writes, depending on what problem you're trying to solve, that sort of thing. But what actually happens internally is you pick the shard key. That part's external. You choose that. Once you pick a shard key, MongoDB will try to balance the data over however many shards you currently have with the goal of keeping the volume of data in bytes equally distributed. So what we do is you pick a shard key, maybe it's the recipient name, something like that. We will automatically start tracking ranges of recipient names, Bob to Charlie, Charlie to Dave, Dave to Fred, that sort of thing. We will pick names, pick data points, pick points in the existing domain of shard key values, with the property that the data that actually lives within those ranges make about the same volume in bytes. In terms of the actual documents stored on disk, have about the same volume in bytes. The goal for each of these things, which we call chunks, which are the storage that correspond to those ranges of shard key values, is to have them be about 64 megabytes in size. You can tune that, but that's the default. And what we do with those chunks is, the chunks are basically just logical units. They're not physical storage areas. Each chunk lives on one shard, but the chunks themselves, if you like, you can think of them as routing information. Bob to Charlie lives here, Charlie to Dave lives here, Dave to Fred lives there. As the volume of data within a particular range gets too big, we'll split it. We'll say, this used to be Charlie to Dave, now it's Charlie to Dan, Dan to Dave. But that split is just a logical operation. It just says, okay, the data still lives in one place, but now we have two ranges, if you like. Eventually, when the system decides, oh, hey, there's more chunks in shard 2 than on shard 3 or shard 1, we'll physically move the data of one of those chunks over from one shard to another, and also fix up the routing that I've been describing, so that to try to keep the volume even. And so the answer to your question is, when you add a new shard, what do? You just move chunks from the existing shard to the new shard, with the goal of keeping the number of chunks about equal. And since we have a separate goal of keeping the volume within each chunk about the same, that should have the property of spreading the volume of data uniformly over however many shards you have. Okay, so that was a lot of words. The goal is keep the data volume balanced. How do we do it? You pick a shard key, we'll track how the data is distributed within the domain of that shard key in terms of volume. We'll track it with the goal of keeping these relatively little chunks of data, and we'll move the chunks of data around to keep the number of chunks uniformly distributed. So if you add shards, we move chunks around. You can actually run a command to remove a shard. That'll drain the chunks back to some of the other shards. And the idea is that each shard, hopefully you pick a good shard key, meaning good, the right things can be targeted, that sort of thing. That means that each shard, therefore, by having about the same amount of data, should give you another unit of capacity to serve reads or to serve writes or whatever. Yeah. Often, it very often turns out to be the case that you have to pick, when you pick a shard key, I'll just be frank with you, that's the hardest part of designing something in MongoDB, is figuring out what is a good shard key. It's probably true with other databases as well, but this is my dog in this race. So, it's probably the hardest thing about designing something in MongoDB is picking a shard key, and often you have to make a choice. Do I care more about the performance of reads, or do I care more about the performance of writes? I've basically never, I can't think off the top of my head of a case where the same shard key would be equally good for both. You usually want to optimize for one or the other, and usually that means you should pick this one or that one. So, just to reiterate, back here, fan out on read, made sending the message very efficient. Just one operation goes to one shard, meaning that I could do, many more of them if I have many more shards. Whereas reading an inbox had to go to all these shards, meaning that by sending the load everywhere, if you like, I basically only get one unit of read operations because the same work is being done in every place. So, yeah. I'm sorry, you had a hand.
Yeah, where do you keep your master sharding routing table? Is that as a master node?
It's totally not in this picture. Yeah, it's invisible. Okay, so if you're really interested, I need that. Okay. Hang on there. Nice. So if you're really interested in what a MongoDB deployment would actually look like in reality, came to the wrong talk, but so each shard, like I said, should have replication going on internally. I can draw a picture of that, but just imagine that this is actually like, I hope this is dry erase. Yeah. So, imagine, let's say a trio of servers, they all have the same data. And then over here, each shard is, like I said, a replica set, trio of servers, this guy has different data, etc. One for each of the shards. Okay, these guys store your actual application data. In addition to these, which are your shards, aka replica sets, there are also, well, this doesn't correspond to anything. There are also some things called MongoS, which are routers. These guys I will not draw. So this is I'm terrible as an artist. This is my admittedly mediocre attempt to draw a cylinder because that's, by union regulation, how you're supposed to draw a database. These guys they don't store any data, which is why I'm drawing them as, it's hard to tell, it's not a cylinder, given how I draw cylinders. It's not a cylinder. And usually you have lots of these. They're totally transient, they don't persist any data. They just route application reads and writes to, one shard or many shards, it depends on the operation. So, you got your data in your shards, you got your MongoS's to route things. How do the MongoS's know where to route things? Which is the answer to your question. In addition to these guys, there are exactly 3, it's like the Monty Python sketch, 1, 2, 3, not 5, 3, what we call config servers. And what do these guys store? Well, basically, they store the routing table that the MongoS uses to send read and write requests. They also store a little bit of other metadata. They're very lightweight. They do need to go somewhere. You need to have 3 of them. And what do they store? They basically store cluster metadata, if you like. Most of which, usually this is like, I don't know, probably less than 100 megabytes of data. Most of it is a routing table. And what's in the routing table? It's an instruction along the lines of documents with the sender Joe live on this shard, documents with the sender, actually they're ranges, so it's like, Joe to Mike lives on this shard, Mike to Tom lives on that shard, that kind of thing. All right. Now you have an illegible, but nevertheless more complete, and certainly quite turquoise diagram. All right, anybody have any questions about that? Yeah.
You're actually adding a shard. Say we go shard 4.
Yeah, sure.
You're updating the routing tables.
Yeah.
In your experience, has that significantly affected performance in terms of reading the application because you're moving around all these chunks?
Yeah, so first things first, we do have, we're not, what do I want to say? I have seen it affect performance. I have seen it significantly affect performance. It's the rare case. We do have some constraints within the system. We do have some safeguards. So for one thing, when we're moving chunks, like let's say you add shard 4 over here, somewhere that you can't see, we have a rule that says the system doesn't currently move more than 1 chunk at a time. So we're not going to flood the system with data migration. That's one goal. Another goal is we keep the data migration actually intentionally slow. So even though we're moving 1 chunk at a time, we actually have a rate limiter in the donor that says don't send more than so many bytes per second. So again, we try not to flood the system with write operations. Because again, I mean, maybe not again, for the first time, actually moving a chunk involves the one node from the donor contacts one node on the recipient side. The donor starts sending data over to the recipient. The recipient receives the data, blah, blah, blah. And then eventually the donor has to clean up its copy of the data. And I'm eliding some stuff. There's actually a complicated 6-stage protocol to make sure that everything is where it's supposed to be and that the cutover of ownership from shard 2 to shard 4 is essentially atomic, and yada, yada, yada. But anyway, never mind the stuff that I'm eliding, or I guess not eliding now that I've told you about it. There's a lot of stuff that goes on there, and there's a lot of attempt to try to keep it under control in terms of performance. Additionally, you can actually tune a lot of things. You can actually slow it down even further than that. There's some stuff that has to do with, I want to tell you about it. There's a thing called secondary throttle. Now that you know what it's called, you can read all about it, and that actually slows it down even more, probably by a factor of like maybe 5 times slower, to reduce its footprint even further. And on top of all that, you can actually turn off balancing if you want to. So you could actually go into your cluster and run a command to say, you know what, I don't want any data to be balanced right now. You can do that manually. You can also schedule a time-based window saying, I only want balancing to happen between 1 a.m. and 5 a.m. So it's only happening during non-peak load times, assuming that those are non-peak load times. I mean, you have to specify the time range. Eventually, the long-term goals for all of this stuff are that the choice of when to balance data will actually take into account how much load is actually happening right now. Right now, it's not very adaptive. We do some things to try to keep it non-invasive, but right now we don't, for instance, have any mechanism or gauging system that says like, oh, if this donor decides that it's too overloaded, it's not even going to participate in a data migration. Eventually, we're going to build that in. At least it's a potential long-term goal. Think long-term, like 2 years, because there's a lot of metering that we would need to do before we didn't have enough information to make that decision. But you have a lot of influence, or y'all have a lot of influence over how this thing works in terms of scheduling, in terms of disabling it, in terms of slowing it down. Now, you asked the question, have I seen it have performance consequences? Yes. But I've only ever seen it have adverse performance consequences in systems that were already overloaded. So here's a truism about MongoDB. It's true of other systems as well. If you wait until you're already redlining to add capacity, it's too late. You should add capacity before you're at 100% capacity.
The four-square lesson.
I mean, listen, that's like ancient history at this point, but it's true of any database, right? I mean, everything that's about to fall over, if you add, if it takes any work to add capacity, it's going to fall over. And that's actually, by the way, not totally what happened before.
Yeah. So really, you need to measure the acceleration and decide.
Yeah, it's a good idea to be monitoring your database.
Who would have thought?
I mean, just generally speaking, what am I doing? Yeah.
So each shard here, in your example that you gave, is single-threaded. So obviously it's more.
So too.
Well, that's when you talk to the example and you had to move the disk, 300 operations.
Oh, sure.
So it was single-threaded. Can you talk about the impact of writes and locking on multi-threaded?
All right. So his question is savvy, but deeper than this. So within a single MongoDB process, so now you're zooming in, it's a bigger cylinder. We have this idea. By the way, this is actually a little bit afield, so if people just want to fall asleep for 5 minutes, that's cool. So we have this notion within a single MongoDB process of separate databases. Database is a set of collections. A collection is a set of documents. So a collection is like a table. A database is like what Oracle calls a schema, or what Postgres calls a schema, or what MySQL calls a database. Each one has a name. So let's say you have a database called, users. You have another database called events. I don't know, something like that. In MongoDB right now, within a single server process, usually a cluster is made up of lots of server processes, but when you're zooming in on just the one, each one of these things has what's called a reader-writer lock. All right, let's see if anybody can remember their undergraduate days. I was quite drunk during mine. Anybody know what a reader-writer lock is? You asked me the question, I got embarrassing it.
Okay, so if you're doing the write, it locks out the reads.
Yeah, right, exactly. So if you look at the Wikipedia article, you get a good overview. The basic idea is a reader-writer lock is a thing that you use to protect some resource to make sure that basically at most one person, one entity, one thread, one program is changing the resource. But if nobody's changing it, then maybe lots of people can look at it, read it. Okay? So what this says is one, let's say readers block writers. Oops. And a writer blocks everything. Additionally, we make a couple of additional choices that aren't standard for the Wikipedia definition anyway, which are that, so that's point one, that's point two. We also say that if a writer is waiting to do something to the resource, then no new readers can start up, meaning that we want to avoid what's called write starvation. Standard textbook definitions of a reader-writer lock will have the property that if you have lots of readers, the writer will never get to do its thing. So we have this idea that a pending writer blocks new readers, which has the property, which has the property that the writer will eventually get to do its thing because everybody yields occasionally. Every operation yields its use of the lock occasionally. And we have some guarantees about this. A reader will never yield in the middle of a document, or a writer will never yield in the middle of a document either. We only will yield on document boundaries. So there's no such thing as a half-written document, or reading half of a document out of the database. What am I talking about? If a writer wants to come in and change 2 fields in a document, change my my title to this and my pay grade to that, probably down in both cases given after this talk. If a writer wants to do that, no reader will see just the demotion and but without the salary reduction. Right? They'll only see both or neither. So, if you put all these things together, what does this give you? It gives you a system that, if you like, prefers writers over readers, because of this idea that pending writers will block new readers, but that also tries to give a fair share because everybody pauses or yields their lock occasionally. So I've been saying 2 different things. I've been talking to you about this data structure that we use internally, and I've been saying that we're protecting a resource. As it happens, the granularity of this lock is database level, meaning that however many collections I have in my user's database, there is a single lock that protects all of them. What does this mean in practice? It means that there is, if you like, there is some absolute number of write operations that can go into the user's database within a single unit of time. It's going to be a function of however long the average write operation takes to go into the user's database. Because at any one moment, there's at most 1 writer going into the user's database. So if the average write operation to the user's database takes 50 nanoseconds, then I can get 2,000 of them per second into the user's database. Now the point of all of that backstory was not that you can go away and say MongoDB can do 2,000 write operations per second. If that's what you heard, you missed all of the stuff before it, so you should just forget that you heard that. So the point of this is, this is currently how our concurrency stuff is implemented. It does have the property that a single MongoDB process will have some upper bound on total number of write operations it can perform per second into a single named database. But you can always add more databases. And then we can get concurrent writes into separate databases within the same process up to as many cores as you actually have. Now, have I answered your question? No is a legitimate answer.
I'm trying to grapple with the cores versus the number of databases.
Well, sure. If I can do 1 write operation at this nanosecond into users, and I can do 1 write operation into events at this nanosecond into events, they better be on different cores.
Okay, and but the 1 lock sits over all the collections within a single DB.
Within a single named database, yes.
Okay.
Sorry.
I think that's actually crucial because it's like a critique that's often brought up, I think.
It is a critique that's often brought up, but it's usually not as justified as the person bringing it up thinks it is. Go on.
Exactly. So the database, so what do you suggest? Keep the databases as small as possible, and if you do, how do you handle like fields that might be in both databases and kind of sit them?
No. You set up a straw man and then you ask for consequences of that straw man. What I suggest is benchmark. Figure out whether, yes, it's true. A single database will have some upper bound on total number of write operations that it can perform. On my laptop, which is 3.5 years old, admittedly with an SSD, but 3.5 years old, that upper bound for a single database is about 25,000 inserts per second. I think that's pretty good for one machine. Is that good enough for you? I don't know. What's your requirement?
But wait, I mean, the thing that I often do, I mean,
Yeah.
imagine you have 2...
You probably read the internet. There's a lot of stuff on
I'm
there.
sorry.
It's cool. What's up? You have 2 collections.
You have 2 collections. One of them is extremely volatile.
Sure.
Let's say logging or web access
Yeah.
or something like that. The other one is like your main data.
Sure.
So if the volatile collection gets continuously hit,
Yep.
your reads are going to continuously, basically always going to get like read logs, right? I mean, like read write logs.
I mean, the way that you're stipulating the question, the answer is yes. So the answer, so the follow-on, so yes, if you are 100% of the time performing write operations, literally 100% of the time performing write operations into a particular collection, then yes, other collections within the same database will be read started. But how do you get to that scenario? Well, you have to be pushing so many write operations into the system per unit time that you are actually hitting 100% utilization of that database. We actually have statistics in the server where you can find that out. What is the percentage of time that I'm doing write operations within this database on average, or within the last second? If anybody here is using the Mongo monitoring service that we offer, MMS, it can actually graph that for you on a database by database level. And yeah, once that number gets, typically for most people's applications, you have a graph and it goes up, and once that number hits like 80%, yeah, you're getting close to capacity. Hopefully you're paying attention to it before you hit capacity so you can add more shards, therefore spread out the load over multiple shards. So, I mean, yes, if you ask me the question, when I'm at 100% saturation, does that mean that I'm at 100% saturation? The answer is, you got it. Yes, when you're at 100%, you're not going to be able to get any more reads. Don't get there, right? Monitor your deployment, one second, monitor your deployment and add capacity before you get there. And then you don't get there. Now, I'm not saying that this is the ideal architecture or the ideal granularity of this lock or anything like that. I'm just saying this is what we have right now. And it's true. People who want to find something that they don't like about MongoDB will say, that's an easy one to find. I don't like it. Okay, fine. You don't like it? Great. Add more shards. That will add more shards and pick a good shard key, spread the load out. On average, whatever the volume is, assuming the volume that you have is, locally, for a short period of time constant, adding more shards will spread the load out over more machines. At least it can if you pick a good shard key. And that, that's basically how it actually works out in practice. Sorry.
So going back to your original example, which was basically, you typically do a lot more reads than
Most
writes.
applications do, yes.
Most applications. And you would use that then for your sharding key to spread things out.
Yeah.
At what point would you actually take into consideration the number of writes as a factor?
When you see that measurable thing about what percentage of time you're spending doing writes, when you see that break some threshold that you decide is your add more capacity threshold, 50%, 60%.
So you would advise basically pretend it's not an issue, put it out there, and then try and then.
So in point of fact, it's actually not an issue.
Right, well,
yes.
Well, that's what I'm saying. Is like, pretend it's not an issue, put it out there, and measure it, and monitor it.
Exactly. In fact, MMS can even send you a text message or an email when it breaks a certain threshold.
What's the threshold then?
You get to pick. So look at it like this.
I mean the actual name.
Oh, it's called lock percentage.
On lock data.
So look at it like this. How fast should your car go?
Sport bike.
You've got a speedometer. At a certain point, it's going as fast as it's going to go. But does that mean that it's supposed to go that fast, or it's supposed to go this fast? I mean, it's kind of a silly question, right? At least you laughed, so thanks. $5 later. Okay. Sorry.
So what's the main purpose of locking the database?
Oh, well, to avoid the scenario where you would see a corrupted or half-written document or something that was otherwise a dirty read.
Belongs to separate collections, right? So they are not basically.
I'm sorry. So actually, I'm not totally sure which question you're asking. Then you're saying, what's the point of having the granularity of the lock in the database, or what's the point of having locks? Oh, well, that's just as far as we've gotten. Right?
Okay.
I mean, hopefully, most of us have made code for a living, and we know that we can't do it all instantaneously. Or if you can, we should hire you, please. Like if you can get all your code done in 0 time.
It was locked for the whole server process.
Ancient history. Ancient history.
Yeah,
I used to have hair too.
That's why we have at BI, we have our main database on one server, and we have our analytics on a completely different server, completely different process, because there was game level locking, and now I can have that.
Right. The granularity of this lock used to be the entire cylinder, but this was now like a year and a half ago.
That's 2.0, right?
Prior to 2.0, yeah. So yes.
Non-technical question. How many slides do you have? Because I want to see.
No. You know what? It's up to you. I have many slides. I wasn't expecting to do all these digressions. So, I can actually skip over whatever you want. I mean, or I could just answer questions and then let you guys go and enjoy the rest of your lives. What do you feel like?
More slides.
All right, then. They're all pretty ugly. I hope you're ready.
Now we can go.
Yeah, you can. But I have to clean some of this mess up now. Goodbye, diagram. Okay, so anyway, back to the idea of scaling. So what is scaling about in the context of MongoDB? It's usually about trying to make sure that whatever work you need to do can actually be efficiently targeted so that the more possible targets you add to the system, the more work can be spread out separately. There are other kinds of applications, right? We're talking about scaling for the web, right? Typical sort of web application is actually, somebody lands on a particular page. That page needs to load a small, selected amount of data. But there's this whole other universe of analytics type applications that are not looking at small amounts of data. They're looking at large amounts of data, typically, to figure some, complicated thing out about that data. Those sorts of applications actually do tend to want this kind of scatter, this broadcast operation, just so that each one is doing less, that the average response time from the shards is going to be reduced. So the world is actually more complicated than just thinking about scaling from this kind of perspective. But anyway, that's just for people that are interested in thinking about it. All right. So another aspect that might be an interesting thing is if you're talking about storing history, retaining certain things, cleaning things out after a certain retention period. For example, you might want to restore a certain amount of inbox history, but clean out the rest because old inbox is like old fish. So you want to retain a limited amount of this inbox history. Sometimes this is required. I don't know if anybody's in any of these regulated or going to be in any of these regulated sorts of environments. But you still want to query efficiently by specific matches or ranges or something like that. So here are a few approaches, and actually one of them is just revisiting something that we've already done. And we have a couple of other features, one of which is new in version 2.4 actually, and the other was new in version 2.2. So same basic idea, we still bucket. So messages to a particular user will go into an array of messages to a particular user. Actually, where'd the recipient go? No, we're done. So same basic idea as before. And then to query for stuff in a particular range of inbox messages, we have this nifty feature that says basically reach inside the messages array, finding the buckets where any of the elements in the bucket matches this weird locution that says the sent time is greater than a particular timestamp. So that's one thing that you can do. Same basic bucketing idea, but you can still do queries by, you can do queries within ranges within whatever is actually in your database, and then actually cleaning things out, removing stuff when it's too old, is just removing messages where the sent is greater than a certain time. We can actually remove them from arrays as well as putting them into arrays. So you're still using buckets. Buckets can grow up to a certain size, potentially. They can also shrink as things are supposed to age out. So what's nice about this, it has the same scaling, it has the same performance, it has the same targetability profile as the previous example. It's basically an embellishment of the previous example, fan out on write with bucketing. But here's how you can implement Ajax. But here's the thing. You end up having this property where eventually you have these old inbox messages that contain, inbox documents that contain no messages after they've all been aged out. So once upon a time, it was being populated with messages, and then as those messages got too old, it was shrinking and shrinking and shrinking, but they're still going to be there. And all that space that they once occupied is going to essentially be fragmentation. And so operationally, you would need to occasionally compact the collection. We have this command, it's called compact. What does it do? It compacts the collection. So it essentially defragments a single collection. So this is one possibility if you're shrinking these documents, or you could actually just delete the document eventually once it's finally empty. You might still end up with some fragmentation over time anyway. So, when you have these documents that are growing and shrinking in MongoDB right now, you do need to think about fragmentation. In MongoDB, we have two different algorithms. I don't want to go into all the details of this because it actually usually takes like half an hour, but we have two different algorithms for deciding how much space a document should take. The default, which tries to be conservative about how much space a document should take, but it ends up being sort of wasteful for certain kinds of workloads in the long run. And then we have this option that you can set that every document, when we put it into the system, no matter how big the document is, should take up space that is some power of 2. Meaning that as the document grows, if there's no room for it to grow into, we make a new space that's twice as big and copy the whole document over into the new space. anybody who's ever had to think about this sort of thing will pretty quickly realize the power of 2 size storage will have the property that space can be more efficiently managed, but on average you're allocating much more space than a document needs. So if that didn't make any sense, we could talk about it sometime. It's very similar if anyone ever had to write like a memory allocator or something like that. Anybody ever does those sorts of things for fun. So that's one aspect of thinking about shrinking and growing documents that will affect performance, because eventually all that fragmented space will take up some memory when it's loaded up into RAM, and it will also take up disk space, which will have some performance properties in the long run. Well, okay. What about, you still want to have a bucket of messages, but we have this new feature in version 2.4 that says push something onto an array of messages, but you can optionally choose to keep them sorted, according, for instance, to the set time, and you can also choose to keep the array fixed in size. So basically, the sort and the slice are independent of each other, so don't worry too much about what the two of them mean. I mean, the two of them together combine in, I hope, an intuitive sort of way, but the main thing is here the slicing. The idea that you can use an array as like a fixed size queue. No, FIFO, yeah. So, the most recent 50, if I leave out the sort, the most recent 50 will stay in there. If I keep the sort in, it's, well, actually, no, same thing, same time. So basically, the idea is that we have this new feature. It's really just an option to the push operator, which we've had for a long time. But the new feature is keep the array sorted according to a particular criterion, and keep the array fixed in size. So this will have the property that no bucket will ever get bigger than 50 messages. And in particular, the oldest one will be the one that gets discarded. So that could be kind of good. It will, with very high probability, avoid those space reclamation fragmentation properties that I described. But how big should the array be to meet a particular retention goal? Right? I said this idea that, pick an array of 50. Why 50? I don't know. Some users might get 50 messages in 1 second. Other users might get 50 messages in a month. If your retention goal is to be based on time rather than based on volume or something like that, this might be tricky to do. You might be able to get it on average. You might be able to get it for 95% of users if you pick a big array size, that sort of thing. It's just something to think about. Now, again, all of this stuff has to do with down-the-line aspects of scaling, which have to do with how efficiently am I using my space, how efficiently am I using my RAM. In MongoDB, it's extremely likely, I might as well just tell you about this, you store your data on disk. So here's some document on disk. In order to actually serve you that document back, it does actually have to be loaded into RAM. And if the document is a certain size, the actual unit of transfer from the disk into RAM is called a page. On Linux and on Windows, these things are units of 8K, except there's this whole other mechanism that says, actually, typically you're going to be loading something like 32K, or sometimes on some Linux distributions, they tune this as high as like 16 megabytes. There's this tunable at the operating system layer. On Linux, it's called read ahead, which says, when I look at this page, the assumption is when you look at this page, you're very likely to look at the next page, and maybe the next one, and the next one, and the next one. And so on Linux, and Windows has an analogous tunable, but I can't remember what it's called. There's this notion of a tunable value by which when one page gets loaded, how many more pages immediately after it on disk will be loaded into RAM. Some recent Linux distributions tune this as high as 16 megabytes, meaning that if you look for a document, you get 16 megabytes worth of memory taken up by the stuff that falls after it on disk, whatever happens to be after it on disk. And so this is where that fragmentation starts to bite you. Because if the operating system is loading this stuff into RAM for us, even though we didn't necessarily ask it to, and most of that is not actually storing your documents, then that's just wasted RAM. And again, performance of a single server is going to influence your performance and your scalability of a cluster. So you care about, to a certain extent, you care about fragmentation, and you also care about tuning down your read. This one is actually sort of a pernicious setting. When it's tuned too high, people end up with like, I have lots of RAM, I have a fast disk, MongoDB sucks. So Why is that? Well, have you checked your read-ahead settings? Oh yeah, you know, you're looking up documents that are like 120 bytes, but you're loading 16 megabytes into RAM for every one of them. Why don't you tune that number down? Yes, sir.
Did you say earlier that the relative timing issue for random I/O and contiguous I/O still exists with solid-state drives?
I didn't say that, and it is sort of true, but sort of not. It varies from from device to device, but go ahead.
Well, that was basically my question.
Oh, yeah.
You didn't say that. Is that true? And you just said sort of.
Not exactly. It seems like the results aren't totally in yet. Solid-state drives can do something like 20 to 40,000 random IOs per second, but different people report very different things about their sequential I/O. MongoDB actually does very little truly sequential I/O, right? I mean, we're either loading a page of index, which means that we're probably just loading like a few pages of index, or we're loading some document data, but very, very little sequential I/O, especially compared to a relational database. A relational database will try its best to minimize the number of disk seek operations and do as much sequential I/O as it can to satisfy joins, up to the possibility of keeping a table stored in order on some join column. Because we don't have joins, by the way, in case anybody doesn't know this about MongoDB, we don't have joins. So, because we don't have joins, we do a lot fewer of that kind of volume of data transfer. But what we do end up doing is a lot more random I/O, which has the property that if you're bound by the quantity of random I/O that you can get, that's going to be a factor. Okay, so the main idea that I wanted to kind of get across with thinking about bucketing is, these things take up space. You might care about fragmentation. You might care about how much RAM is going to be used, that sort of thing. We have this other feature. It's been around since version 2.2, where you can actually say, you can actually tell the database to automatically clean up data, clean out documents, delete documents once they've gotten past a certain expiry date relative to now. And so by modifying the bucketing, so that instead of storing a sequence number, I'm storing a sequence time, like the time at which this particular sequence was most recently updated. And by creating a special sort of index with this flag expire after seconds, it's basically telling the database, once a bucket has gotten so old that there's nothing in it that the sequence number is more than this number of seconds old, delete the whole bucket. And the database will do that for you. So this will end up saving you some space. It will also have this nice property which has another impact on scaling, which is the actual cleanup of this is a low priority background thread that's running all the time in the server, as opposed to a batch job that runs at midnight and pummels your server for an hour, cleaning things up that you probably haven't looked at in a year. So yeah. Anyway, this is a somewhat minor kind of example of one of the things that comes up a lot in systems, especially once you've gotten to the idea of fan out on write. Once you get fan out on write, you are actually storing more data, right? Because you're storing multiple copies of the same message. So you probably want to clean things out eventually. Okay. This was a specific example. I have one other example, totally unrelated to these two things, which having to do with multiple identities. If you want to sort of think about people having different handles coming in from different source systems, does anybody want to think about that? Sure. No is a legitimate answer. All right, so what's the goal? So you want to look people up by different kinds of identities. Their username in your system, their email address, their Facebook, their LinkedIn, whatever. Typical kind of thing. So what are a couple of approaches? Well, you can have one document for your user with all their identities in one document, or you could have not. So single document for a user might look something like this. Joe. So this is Joe's username in my system. There's email, there's Facebook, there's LinkedIn, etc. In this case, if you distribute the data according to the underscore ID, which I'm using as the ID in my system. In MongoDB, for anybody who's not familiar with it, underscore ID in our system serves as a primary key. It's a unique identifier of a document within a collection. So, I'm basically saying, well, I got a Joe, here's his identifiers in some other systems, and I want the data to be parceled out according to his identifier in my system. And I want some secondary indexes on these other fields. You can do that in Mongo. Mongo allows you to have a number of secondary indexes. I say a number. The number can't be bigger than 63, but whatever, it's a number. I took enough math to know that that's a number. So if you're retrieving a single document, well, that's targetable, that's nice. So looking somebody up according to their identity in my system is a targeted query, meaning that this shard could do a different one at the same time, and this shard could do a different one at the same time. Actually, many of them could happen within each shard as well. But to look somebody up by their email address comes back to one of these scatter-gather queries. So, which one is more common? Looking him up by his ID in my system or looking him up by his ID in some other system? Hard to say. What if they're equally common? Right? I said something earlier with malice aforethought. I've done this once before. I said something earlier that you usually want to pick optimizing for this or optimizing for that. In this case, maybe we don't want to do that. Maybe we want to pick a solution that's actually going to work okay for all of them. So, okay, everybody get this? Scatter gather versus targeted. Okay. So, again, look up by a shard key for a single value is going to be routable to one shard. So looking up a constant value of the shard key, a single constant value. A range of shard key values might go to multiple shards, but a single value might go to one shard. But looking up by that other stuff that isn't the shard key is a so-called scatter-gather. Additionally, this is a restriction in the system. Any secondary index, any secondary keys cannot be unique globally. What does that mean? That means that I cannot enforce uniqueness of joe@example.com. I can't say that there's just one user who has that email address. I can say that there's just one user named Joe in my system, but I can't enforce uniqueness of those, that there's no more than one user with a particular email address. Okay, so what if I change it up? What if I say each identity in some system gets a separate document? For example, I'll have a collection called identities, an identifier. His handle in my system will be Joe, and maybe this will be his internal user number, and then his email address will be joe@example.com, and again, same user number, and his LinkedIn will be Joe E. Smith, same user number, and I'm sharding on this unique identifier. In this case, I'm basically just adding one level of meta, right? I'm saying that instead of sharding on his username in my system, I'm sharding on something that refers to which system is it, my system, the email universe, the LinkedIn universe, and the value. So I'm sharding on this whole document. So before I said that you could shard on things, I didn't say this, but I was giving you examples where I was sharding on a string. You can actually shard on compound documents like, these constructed documents like Joe E. Smith, email joe@example.com. Now that's my identities collection. So each different identity will go into a different small document. And then my, that's the shard key. Now, because I'm picking this as the shard key, I can have a unique identifier, a unique index on it. So secondary keys other than the shard key cannot have the unique index, but shard keys can have a unique index. So that's nice. So I can enforce uniqueness, that there's only one person whose email is joe@example.com and one person whose LinkedIn is Joe E. Smith. And additionally, I'll have a users collection that's sharded on my internal IDs for these people. And that's how that's going to work. So what does this look like? To actually do a lookup, to actually find the information about my user based on his, let's say, email address or something like that, or something, I have to do two queries, but each one of them is going to be targeted. So what's the point here? Well, my previous example had some limitations. Certain lookups were privileged, other lookups were less privileged. This example is going to be equal for lookups based on my internal ID for him or the external IDs, like from LinkedIn or from the email namespace, but at the cost of having to do two reads. However, each of those reads is targeted, meaning that, again, it should scale linearly with the number of shards that you have. Yes, sir?
Is there a Mongo tool that's analogous to MySQL's explain query?
Well, yes, we call it explain. In MongoDB, if you start up the shell, I don't have any queries here that do this, but instead of saying, well, save puts a document in. We also have an insert, which puts a document in. If instead of this you said find, and then tack on .explain, you get back an explain plan. Our explain plans don't look like MySQL's explain plans, but they can actually be learned and understood. We even have documentation. It's amazing. Which you might take a look at to figure out what all the fields mean, that sort of thing.
And would that be potentially, would that tool be potentially useful for creating a good sharding strategy?
Yes, though more interesting than explain would actually be a holistic understanding of what the dominant access patterns are. What explain will tell you is, what does this query do? Not which is the most common query or which queries are most business critical, you know? That sort of thing. All right, so I'm clearly quite over time, but only by about an hour. The conclusion, I hope, is that there are usually multiple ways to do it in MongoDB. This is good or maybe it's bad, I don't know. You need to understand the key use cases of your application and try to balance between, well, I would actually say, yeah, balance between not necessarily the performance of the query versus the performance of the write. Typically,